Okay, I'm going to work through this homework showing how to get these problems done. First thing I'm going to do on this first problem right here is, let's expand it. We're going to copy over the structure and put it right here. Now what does the sodium hydride do? Well, it removes the proton and leaves a negative charge behind on the oxygen, which then, because this is primary, can do SN2. So I'm going to take this part of the compound. Let's just copy it. Okay, and I'm going to take that part of the compound and paste it here. Now I need to make sure it connects. So I'm going to flip it over and connect it to that oxygen. Okay, so it actually makes an ether. The reason that it does not do E2 is only SN2 can occur on this compound. There's no double bond can form here, so it doesn't matter how basic this gets or even how slow this SN2 goes, it's still going to only do SN2. Notice because it cannot form this alkene, but it's primary, so an SN2 would go quickly. Here's a hydrolysis. Let's name this compound first. The name of this compound is going to be an ether, and we can call this ethyl, and we call that isopropyl, and we would put them in alphabetical order. Ethyl, isopropyl, ether. Okay, that could be the name of this. That's one name. Another way we could do that is name the longest chain here, which would be methyl ethyl. And we can say ethoxy, ethoxy, and then it's going to be on the number 2 carbon. So it would be 2-ethoxy, 2-ethoxy, and then it would be propane. Because the longest chain is not the ethyl, it's a propyl here. Okay, 2-ethoxypropane. We're going to cleave this now with hydrobromic acid. What does this do? It protonates this oxygen, and then we look to see what can it do, SN1 or SN2. You only have a primary and a secondary here, no tertiary, and so the SN2 is going to be the mechanism that causes it to cleave. So I'm going to copy this and put this on the other side. Okay, so this is my ether. I'm going to cleave it. Which side is, if this gets protonated, which side is SN2 going to occur on? It will occur here. So I'm going to cleave that away from the oxygen. This now will have a hydrogen attached. The hydrogen, oops, grabbed the wrong thing. The hydrogen from the hydrobromic acid actually is attached there, and then the bromide ends up over here. All right, if I look at this compound, this is going to do a cleavage also. To name this is a little harder to name because we've got this double bond in here. Let's name this as propene. This other group right here can be named as either sec-butyl, or we can say 1-methylpropyl. So let's go ahead and type in the name. We can say 1-methyl, excuse me, I didn't put a 1 in there, 1-methyl, and then it will be propoxy, And then we will want to make it propene. But that's on the number 2 carbon. So we have to put a bracket in here and a bracket here and make that on the number 2 carbon. So that would be 2-1-methyl propoxy propene, or another way we could do it using the sec-butyl idea, we can say 2-sec-butoxy propene. Let's make that sec to make it. Okay, so now let's go ahead and see what happens when we hydrolyze it with hydrobromic acid. When we hydrolyze it with bromic acid, the hold on just a minute. The oxygen here will become protonated, and this becomes a good leaving group. If we look at this carbon, it's secondary. If we look at this carbon, it's vinyl. You cannot have SN1 nor SN2 on a vinyl carbon. So what must happen? The oxygen must, oh, excuse me, the wrong way. The oxygen must remain attached to the vinyl. And when the oxygen is protonated, it remains, the alcohol remains on the vinyl carbon, and the bromine is able to do a slow SN2 on the secondary carbon. Okay, let's move over now and do these reactions, and I'll slide up a little bit. Okay, what we're going to do is look at what will sodium hydride do to this compound. The fastest thing for it to do is deprotonate this oxygen. It's a strong enough base that it'll readily deprotonate this oxygen. When it deprotonates this oxygen, let's go ahead and copy the structure over there. So when we deprotonate this oxygen, it then has a negative charge. And remember, if a ring can form, it will. This oxygen with a negative charge on it right up here will be able to do an SN2 on this chlorine here. It's not going to do any kind of elimination because the SN2 is so readily encouraged by ring formation. So this oxygen is going to come over here and displace this chlorine. So let's go ahead and see what happens there. That's going to make 2 carbons and then an oxygen attached to this location. So I'm going to take this away. I'm going to put the oxygen in place there. And then what I'm going to do is bring 2 carbons over to it. Let's make that a little less severe. We're going to bring 2 carbons over to it to form that ring. Down here we've got hydrobromic acid. What does it do? It does ether cleavage. What will happen, oops, let's copy this over to, oops, that's not copying. We're going to copy this over here to this side and realize that this oxygen gets protonated. Let's look and see what either carbon can do. This is a tertiary carbon. That's a primary carbon. Well, tertiary carbons are going to do a fast SN1. So the first thing we know is that the bromide is going to be located there. So let's just flip this over and put the oxygen. Oh, that doesn't work. Okay, let's just put the oxygen over here like this. Take that away and put a bond over to the oxygen. Now the hydrogen has to be attached to it because it was protonated. Recall that? And it's doing an SN1. So this is basically the leaving group. And this is where the oxygen used to be, and now the bromide will be there. All right, and down here, let's look and see what happens here. This is an alcohol that can be deprotonated by this. If I deprotonate this and put a negative charge here, so we're going to put a negative charge right there, what's going to happen? Well, a ring actually can form here because this is set up so close, and even though it'll make a strained three-membered ring, if there's no water around, it actually can do a ring closure and do an SN2 on this carbon here. So this would be my leaving group. It leaves, and this oxygen actually ends up attached to both carbons. Okay. And so these two things are attached there. And of course, it would be underneath because let's increase the density of these lines. Okay. And those lines, these bonds are on the other side because that's where the oxygen came from. So let's go ahead and put some back behind, draw those in so it's a dotted line. It's not, you can't see it very well, but you get the idea. So it will be going behind. Okay. Now what we're going to do is look at this problem. Again, sodium hydride is going to deprotonate this. So let's go ahead and copy this over here. So we'll deprotonate this. And we'll put a sodium there. Okay, so that's now a very basic nucleophile. Now, where is it going to do? What is it going to attack? It's going to attack this. Okay, so let's put this over here. What kind of leaving group do we have? We've got a very good one. It's a bromine, but at the same time, it's secondary. This is very basic in addition to being a good nucleophile. So what's going to happen? You're going to get E2, and the hydrogen that is attached here will be plucked off by this. This is going to return to the alcohol state, and we're going to get this as one product. And when this proton is removed, this bromide is going to leave, and we're going to get this alkene. Oops. Okay. What is the product? Well, of course, it's going to be the alcohol. We can name the alcohol. The name of this alcohol will be cyclopentyl methanol. And the name of this product will be cyclohexene. Both of those you know how to name.